good morning. So a new link has been given to you. Whether people have informed your friends to join the class. Okay. Since power is not there, we have changed the mobile. So therefore new link has been given.
Ask them to send their names, whoever is there in that. And you just request whoever is there. If
No, they have sent the good morning
they
message.
send,
Okay. So what I will do is, I'll start with the class. So meantime, you can inform your friends also to join the class. Okay. So we are going to start with the new topic, that is D and F block elements. Okay, we are going to start with the new topic which is called as D and F block elements. Fine. Now, in the name itself it is there. It is related to those elements which are present in this particular block, which are called as transition elements, right? So D and F block element, especially D block, they are called as transition elements, and F block, it will be called as inner transition elements. It will be called as inner transition elements. So altogether we can call them as transition elements. Fine. Now first we'll focus on D block elements. F block element later we can concentrate. Now when it comes to board exam point of view, with respect to board point of view, from this particular chapter you can expect 5 to 6 marks question. You can expect 5 to 6 marks. Normally they will go for 5 marks and all. So it will be asked for 5 to 6 marks. In that, one will be with related to 3 marks question, that is related to preparation of KMNO4. So it is related to board exam point of view, where you can have 5 to 6 marks question. In that, 3 marks question will be on preparation of either potassium permanganate or potassium dichromate. Okay. Anyway, we are going to study all those things in detail. So this is related to board exam, and when it comes to competitive exam, you can expect 2 to 3 questions from this particular chapter. When it comes to competitive exams, you can expect 2 to 3 questions. Fine. So that's where weightage for this particular chapter. Okay, since you people have already studied coordination compound, some of the properties or some of the concepts related to D and F you might have already discussed in those coordination complex compound topic. Fine. Now, as I was telling, D and F block, where D block elements we are going to focus now, which is also called as transition elements. So can anyone tell me why D block element should be called as transition element? What is the reason? First and very important thing is, what do you mean by D block elements? Because in the periodic table we have the S block, P block, D block and F block. Now S and P block element in second year only people have studied. Now with respect to D block, why they should be called as D block elements? Any one of you? Why it should be called as D block? So that is because in these compound or in these elements, in their elemental form or in their ionic form, in their elemental or ionic form they will be having incompletely filled D subshell. They will have incompletely filled D subshell. incompletely filled D subshell. That's why they are called as D block element. Fine. Now, when it comes to P block, we used to tell that these are the group of element where P subshell will be getting filled up. That's what we are going to tell. But here, if you observe it carefully, here we have mentioned that in their elemental form in that they are in the atomic form, in their neutral category, or in their ionic form. We are mentioning that in their ionic form. So that means either here in their atomic condition or in their ionic form condition, they should have the incompletely filled D subshell. So that's what we are focusing here. So there is a reason. So which you are going to understand why we are mentioning ionic form once again. So for that you are going to get the answer when we are going to talk about these elements in detail. Okay, very shortly we are going to discuss. Now when it comes to D subshell, we have 3D series, then 4D series, 5D series and 6D series. So total when it comes to D subshell, we have 3D series, 4D series and 5D series elements. Okay. So these are the different periods. These are the different periods which belongs to transition element, that is D block element. So period number 3, period number 4, period number 5, period number 6. Okay, all of you have understood? So actually it is period number 4. Okay, period number 4, 5, 6, 7. So no one is responding. So whether they are getting, no one is responding. It is period number 4, 5, 6 and 7. So that's where we have the period number. I will write it here. So period 4, period 5, period 6, period 7. Okay. So period number 3, there is no D block element. In period number 3, there is no D block element. It will start from period number 4. That's what we can observe here. Whether all of you are seeing the board? Fine. So all of you are getting it, right? So that's where we have period number 4, 5, 6 and 7. Once again I will repeat. I told period number 3 it will start. But it's not from period number 3. It's from period number 4. D. It was off. Okay. So all of you are getting it, right? So that's where we have the period number 4, period number 5, period number 6, period number 7, 3D series, 4D series, 5D series, 6D series. Why it is happening? That one you can understand by using off-board diagram. So that's where 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, like that it will goes on. Right? Of board diagram. Now, according to this, according to whatever picture I have written, according to this, at energy level 3, D subshell is available. Right? At energy level 3 itself, D subshell is available. That means period number 3, because in the periodic table, each period talks about energy level, right? So period number 1, that means we are talking about energy level 1. Period number 2, that means we are dealing with the energy level 2. Period number 3, we are dealing with energy level 3. Like that, we have got the different energy level. I am talking about outermost energy level. Fine. Now in that case, when it comes to 3, I can say there is availability of D subshell, but still it starts from period number 4. That is because of the off-bow principle, where after 2 years we have 2p, and after 3 years we have 3p, then 4s, then comes the 3d, then comes 5 years, then comes the 4d. So what is happening here? Here, once 3p is getting filled up, it's not moving to the 3d, it is moving to the 4s. That means we are moving to the next energy level. So we are not in energy level 3, we are in energy level 4. Then only 3d is getting filled up. Once 4s is going to fill up, then only electron will enter into 3d. Now, once 5s is getting filled up, then only electron will enter into 4d. Once 6s will get filled up, then only comes the 5d. So due to that, because once 4s is getting filled up, since 3d is coming into the picture, so therefore it belongs to period number 4. Once 5s is getting filled up, then only 4d is going to get filling up. Therefore, it comes under period number 5. Which one? 4d. Same logic is applicable for 5d and same logic is applicable for 6d. So, always remember that transition element, that is D block element, the period will be starting from the period number 4. And we have how many types? We have 3d series, 4d series, and 5d series and 6d series. Okay, so in that it will start from group 3. It will start from group 3, then it will go up to group 12. It will go up to group 12 because group 1 and 2 belongs to alkali and alkaline earth metals, that is S block. Then group 13 to group 18, it belongs to P block elements, right? So that's where we have group 3 to group 12. So how many groups will be there? How many groups? 3 to 12 means it should be 10, right? Because D subshell can accommodate how many electron? D subshell can accommodate 5 electron. If you remember, we used to draw this particular box to show the filling of electron, right? So there is availability of 5 orbitals in the D subshell, each orbital 2 electron. So maximum 10 electron it can accommodate. So therefore D block, each series should have the 10 elements. It should have the 10 elements. But when it comes to 5d and 6d, period number 5d means period number 6. 6d means period number 7. When it comes to these two, it looks like more elements are there with respect to atomic number. That is because in between we will be having F block elements. In between we will be having F block elements. Observe here carefully. So once 5, 6s is getting filled up, before coming of 5d, there is an entry of 4f. Right? There is an entry of 4f. So that means when it comes to 5d series, in between we have to talk about filling of 4f also, right? So that's where the position of F block. When it comes to 6d, observe here carefully. Before entering into 6d, once 7s is there, before entering into 6d, 5f has to be filled up. So therefore, when it comes to period 6 and period 7, that's where we have in between F block elements also, whose position has been located at the bottom of the periodic table, not to disturb the transition element. That is the reason why F block element have been shown at the bottom of the periodic table. Otherwise, it looks like some of the D blocks are present here, some of them they are present on the extreme right side. So to avoid that confusion, to maintain the D block in a rectangle shape in one position. They have placed F block element at the bottom. Anyway, in detail with regard to the F block element, we are going to discuss it later. But these things you should be remembering. Right? So what I mean to tell you is each series will have the 10 elements. Each series they will be having 10 elements because D block they can accommodate maximum 10 electrons. Fine. So in that way, if I take first series, it will start from scandium to zinc. It will start from scandium to zinc. Okay. Same way, when it comes to second one, can anyone tell me? It will be what is Y? Y is yttrium, right? So it will be yttrium to cadmium. Next one, lanthanide series. It will start from or after lanthanum. So that's for here we have the lanthanum. After that we have the F block. And once again these block elements will start. Right? So from lanthanum to mercury. From lanthanum to mercury. Then actinium. From actinium to any one of you? From actinium to Copernicum, Cn, Copernicum. So that's where we have the different series. In one of the competitive exam they had asked, they had given the option and the question was among the following which belongs to 4D series or some this series only they had asked. Among the following 4D series belongs to, and they had given these type of options. In that you have to select. Fine. So that's where we have the scandium to zinc, yttrium to cadmium, then lanthanum to mercury, then actinium to copernicum. Now, one thing I will make it very clear. Most of the element in period number 7, they are synthetic and they are radioactive in nature. Most of the element, especially copernicum, borium, they are all present here. All of them, they are synthetic and they are radioactive in nature. They are radioactive in nature. Please remember this. Most of the element which belongs to period number 7 in the D block, F block we are going to discuss, no doubt. In the D block they are synthetic and they are radioactive in nature. Fine, all of you have understood. So in that way we have scandium to zinc, yttrium to cadmium, lanthanum to mercury, then actinium to copernicum. That's where we have the 3D series, 4D series, 5D series, 6D series. That's where we have period number 4, period number 5, period number 6, period number 7. All of you have understood? So why they should be called as 3D series? Because 3D subshell is getting filling up. Why they are called as 4D series? Because 4D subshell is getting filled up. That's where it is applicable even for 5D and 6D. All of you have understood? So in that way, how many elements are there in each period? 10 elements are there. So how many periods are there in D block? 4. So how many elements should be there in D block element? Total element. It will be 40. Each 10 elements in each period. So we have total 4 periods which will be including D block elements. So how many elements should be there total? 40 elements should be there. Now, when it comes to these elements, we have copper. We have the copper. I will take common example. We have the copper. Can anyone tell me what is the atomic number of copper? It is just before to the zinc. Can anyone tell me how many? What is the atomic number? It will be 29. Atomic number of copper will be 29. Can anyone of you write the electronic configuration of Bohr diagram is here? Yes, Srishti, it is 29, no doubt. So now, can you write the electronic configuration for copper? See, when I am talking about inert gas, we have helium, neon, argon, krypton, xenon, radon. Right? So if you are getting confused, you can write this 2, 10, 18, 36, 54, then 86. 86. So that's where we have the inert gas elements. Of Bohr diagram is that write the electronic configuration for copper. So copper is 29. That means we should use the help of, or we should take the help of argon, because argon is the last element in period number 3 and copper belongs to period number 4. So that's where argon. Now 18. So 29 minus 18, it will be 11. So rest of the 11 element you have to fill it up. So when I am talking about argon, period number 3, right? So that means up to 3p I have finished. I have finished the electronic configuration up to 3p. Then I have to talk about 4s and 3d. So 4s and 3d, or I can take 4s on the outside because of higher value. So 4s. Can anyone? 11 electron, we have to fill it up. So it should be 3d10, 4s1. Right? So that's where we have the copper electronic configuration. Now if you observe here, D subshell is completely fit. Right? D subshell is getting completely fit. But still copper is called as D block element. That is because one of the ionic form, stable ionic form of copper is +2. That's not related to electronic configuration. That is related to hydration enthalpy. Anyway, we are going to discuss later. So that's where I have the cupric form of the copper. We have the cupric form. So in that case, what should be the electronic configuration for cupric ion? So it will be argon 3d9 4s0. All of you will agree? So 2 electron is not there. So 3d9 4s0. Sir, 3d10. It's not, it was there stable. Now it became 3d9. So in that case, if I take cuprous, Cu plus, so electronic configuration will be argon 3d10 4s0. So in that way, cuprous should be stable, no sir, because it is having stable electronic configuration. Yes, if I compare cuprous and cupric, no doubt, cuprous will be having stable electronic configuration, but still, cupric will be more stable in the solution. Cupric will be more stable in the solution. That is because of the higher hydration enthalpy. Right? So what I mean to tell here is, if I take copper, which is a D block element, example for D block element, it belongs to 3D series. Among the D block element, it belongs to period number 4. It is having electronic configuration as 3d10 4s1. Cupric ion 3d9 4s0. Cuprous 3d10 4s0. That means cuprous and copper, they have the completely filled D subshell. But when it comes to cupric, it is having incompletely filled D subshell. So that's what I was telling in the beginning of this particular class. When we were defining the D block element, we have defined it as these are the group of element which will be having incompletely filled D subshell either in their elemental form or in their ionic form. That's where it is applicable. In their one of the ionic form of copper, they have the incompletely filled d subshell. So therefore, it belongs to d block element. It is considered as transition element. All of you have understood? That is one thing. Now, I will come to neighbor of copper. Any doubt in this? No doubts, right? If you have any doubt, you can ask. Or if you move to the next element, neighbor of copper, that is zinc. Zinc is having atomic number as 30. Atomic number as 30. What should be the electronic configuration? Argon, I have kept it like as it is. Now we have to start filling the electron. Now it will become, any one of you, now it will become 3d10 4s2. You can write 4s2 3d10. That is also fine. Absolutely correct. No doubt. Okay, na? So we have 3d10 4s2. Now we have completely filled the subshell. We have completely filled D subshell, where in zinc we have the completely filled D subshell. Now, zinc can show only one ionic form, that is zinc plus 2. There is no question of zinc plus 1 and all. It will show only zinc plus 2 ionic form. Okay. So what is the electronic configuration here? It will be argon 3d10 4s0. Right? Say 3d10 4s0. What you people are observing with this example? Same thing can be applicable even for bottom element, that is cadmium. Same thing can be applicable for mercury. Okay, copper nickel, fine. Anyway, we are not going to discuss. It's a radioactive. Zinc, cadmium or mercury. Same logic is applicable. Now what is that? What you can observe here? So whether it is in elemental form or in ionic form, they have the completely filled d subshell. Right? Unlike copper, where in elemental form it was completely filled, but in one of the ionic form, Purnima, what is that S subshell you wanted to tell? Okay, you wanted to tell that S subshell is 0, means no electron in zinc plus 2, right? Yes. So what I mean to tell you is, what is that difference between copper and zinc, which you can observe? That difference here is, when it comes to copper, in elemental form, yes, D subshell was getting completely filled. In one of the ionic form, that is cupric form, Cu plus 2, there were incompletely filled D subshell. But when it comes to zinc, as I told, there is no question of zinc plus 1 or plus 3, only plus 2. But when it comes to zinc, we have completely filled D subshell, and zinc ion, that is zinc plus 2, we have the completely filled D subshell. Now, whether we can call it as a D block element in that case, according to definition, no. No, sir. Zinc, cadmium, mercury, they cannot be considered as D block element in that case, because on all this condition, they have the completely filled D subshell. But still, they are included in the D block. They are included in the D block. Right? Same as that of the inert gas in P subshell, alkaline earth metals in S block. So same here also we have the zinc, mercury, cadmium and all, they included in the D block, although they have the completely filled D subshell. Right? Now, since this is the condition, why they have included these elements in their respective block? Because of the similarity in their properties. Due to the similarity in their properties. Now, these set of element which belongs to group 12, this set of element which belongs to group 12, they are called as pseudo transition elements. They are called as pseudo transition elements. Okay, so that's where we have the important point. That's where we have the pseudo transition elements. Now, what are pseudo transition elements? So these are the group 12 elements. These are the group 12 elements which are having completely filled d subshell in their elemental or in their ionic content form. So therefore they are called as pseudo transition elements. So which is that example? Example here is zinc, cadmium, mercury. Any of these three can be utilized as a example. All of you have understood? Any doubts? Any doubts? In that case, shall we move to the next one if you don't have the doubts? Can anyone write the electronic configuration for manganese? Electronic configuration for manganese. It belongs to same period, that is 3D series, period number 4. Can any one of you write the electronic configuration for manganese? You can try it out. Group 7, it belongs to group 7. Yeah, group 7. All of you have written? Fast, fast. Naturally, we should take the help of argon. What is that? Next. Argon means up to 3p is done. What is left over? Argon atomic number is 18. So 25 minus 18. How much it will be? It will be 7. Right? So in that case, we have to fill those electrons in their D and S subshell. Okay, Purnima, how you got 3D8? 25 minus 18 is? It should be 7. So 3D8 cannot come. It will be 3D5 4s2. 3D5 4s2. Right? That's where we have the manganese, one of the element which you will come across very often. Potassium permanganate and all will come across now. So that's where we have 3D5 4s2. Yes. So that's where we have the stable electronic configuration for manganese and that element group elements. That is group number 7. So where they will be having half filled D subshell, where they will be having half filled D subshell. All of you have understood? So that's where we have the manganese and rest of the element which belongs to same group. Remember about the manganese. Okay. So any doubt in this? So now, when I am talking about physical properties, now I am coming to the D block element. Remember about this. I will come to physical properties. Now, physical property is nothing but melting point, right? So boiling point, they are all comes under physical properties. Since we are dealing with the transition element, why they are called as transition element? That should be answered first, right? So why they are called as transition element? Why they should be called as D block elements should be called as transition elements?
Because electron transitions into the nano.
That is because they are located, if you see the periodic table, if you recollect the periodic table, D block elements are located between the metals and the non-metals. In the periodic table, metals are S block element, right? So non-metals comes under P block elements only. Only in P block we have the non-metals. So therefore, since these transition elements are present between metal and non-metal, there is a transition in the property. So there is a shift in the or transition in the property from metallic to non-metallic character. So therefore, they are considered as transition elements. Fine. So in that case, when I am talking about physical properties, all of us we know that in the name itself it is that transition metals. All of them they are metals. That means all of them or most of them should be in solid form at room temperature. Mercury and all they are the exceptions. So they should be in solid state. Therefore, we are going to majorly focus on melting point. So when it comes to D block elements compared to S block element, they are a bit hard. They will be having higher melting point. They are not like soft as that of the sodium and all. So these transition element, they are a bit hard. All of us will know iron rod. Whether they are soft, by using knife we can cut them? No. But if I take sodium and all, they are soft metals. So that's where compared to alkali and alkaline earth metals, transition elements they are a bit hard. They will be having higher melting point. Fine. So what can be the reason why they should be having higher melting point? That question has to be answered now. Why transition metals will have the higher melting point or higher atomization enthalpy? So what do you mean by atomization enthalpy? Atomization enthalpy means amount of energy required to separate the elements from each other. That is called as atomization enthalpy. Okay. So amount of energy required to separate the elements from each other, because in a solid state they will be having many elements which will be together. So that's where we have the atomization enthalpy. So along with that, they will be having higher melting point. Now, what is the reason why transition element will be having higher melting point or higher atomization enthalpy? What might be the reason? Think and tell. Should be there. So that is because they will be having incompletely filled d subshell, which will make high amount of interatomic interaction due to the incompletely filled d subshell, which has higher interatomic interaction, higher interatomic interaction. Okay. So please remember, when I am talking about metals, they are all having metallic bonds, right? They are all having the metallic bonds. If you recollect first year topic, atomic structure. So those electrons which are present in the S subshell, they are close to the nucleus. They will be having higher nuclear force acting on them. Then comes the P subshell, which will be having bit less compared to S. Then comes the D, which will be having less compared to P. So what I mean to tell here is, those electrons which are present in the D subshell, they will be feeling less nuclear force. So due to that, what will happen in the crystal structure? In the crystal structure, that electron which is present in the d subshell, since it is having less nuclear force, same amount of nuclear force it can act felt by the neighboring nucleus also. So that's what these electrons are the one which can be easily involved in the metallic bond because they are loosely bound to the nucleus. So that's where we have the transition elements due to the presence of metallic bond, due to the presence of higher interatomic interaction, they will be having higher melting point. They will be having higher atomization enthalpy. Right? So due to the presence of metallic bond, they can be good conductors of electricity. Right? They are good conductors of heat, thermal conductors, and they are very good conductors of electricity, that is electrical conductors. So that's where we have the transition elements. Fine. So among the transition element, tungsten, chromium and all, they are the one which will be having higher melting point. They will be having or they demands higher energy, tungsten and all. That is due to the incompletely filled d subshell present in them. If you go to the extreme right, from in the d block pairing from scandium, if you are moving to the zinc, extreme right element they will be having less melting point. Towards you go towards the right side, they will be having bit less melting point. That is because d subshell is getting paired up. Electrons are getting paired up. So as there is increase in the unpaired electron, this property is going to increase. That is melting point or atomization enthalpy is going to increase as there is increase in the number of unpaired electron. I am expecting a question. I told tungsten, chromium, they are the some of the example, or molybdenum, they are the some of the examples which are having high atomization enthalpy or melting point. But if you observe, manganese is the one which is having high amount of unpaired electrons. D5, manganese is having high amount of unpaired electrons. Then why not manganese is dominating? Any one of you? Why not manganese is not going to dominate? Why other elements which comes before the manganese, they are the one which are having higher atomization enthalpy? What might be the reason? Because if I go with number of unpaired electron, it is more with respect to manganese, not with chromium, not with molybdenum, not with tungsten. Because chromium is 24, just before to the manganese. But chromium is going to dominate, not the manganese. What is the reason? That is because in manganese, it is having half-filled d subshell where they are symmetric, electrons are stable with stable electronic configuration. So due to that, interatomic interaction is going to decrease. Interatomic interaction is going to decrease, which is not there with respect to chromium and all. As the same way when you are moving after manganese and all, although there is a slight increase or there will be slight variation, but still they cannot across the manganese chromium and all, means chromium molybdenum and all, they cannot beyond that. They will be below that only because as you are moving rightward, there will be initiation of pairing of electrons will takes place. Once you cross the manganese, that is group 7, if you move to 8, 9, 10 and all, so there will be pairing of electrons will start. So therefore, those elements which comes after this, they will be having slightly less melting point and all. Right? So which is that one which is having highest melting point and all? That is chromium, tungsten, molybdenum. So these are the some of the examples for the transition element with higher melting point. All of you have understood? But all together, if I observe, that's where we have the physical properties where transition elements are going to dominate over the S block element. Any doubt in this? 2 points we have discussed here when it comes to physical properties. One is transition elements. Dominate over S block element in their physical properties. Dominate over S block elements in their physical properties. But please remember, I am not talking about the reaction. Please remember, S block elements are the one which can donate the electron easily compared to transition metal. I am not talking about chemical properties. I am talking about physical properties. When it comes to physical properties, yes, transition element will dominate over the S block element with respect to melting point and all. Okay, so that is one point which we have discussed. Now, next point here, what we have discussed here is tungsten, chromium, then molybdenum. So these are the element which will be having higher amount of atomization enthalpy or melting point. They will be having higher melting point, okay, compared to other element in their respective period. And chromium is next before to the manganese. It is just before to the manganese. That means period 3D series it belongs to. Fine. So any doubt in this? Any doubts? So if you don't have any doubt, I will move to the very important concept. I will call it as very important. That is Lanthanoid contraction. That is nothing but Lanthanoid contraction. Okay. So now, when it comes to Lanthanoid contraction, what do you mean by Lanthanide contraction? What you can understand when I am telling Lanthanide contraction? What you can tell? If I take 3D, 4D, 5D and 6D, right? So 3D series, 4D series, 5D series, 6D series. So what you expect with respect to their atomic size? Naturally, it should have been increased like this, right? That's what our expectation. There is an increase in the atomic size. So this is 3D series, this is 4D series, this is 5D series, and this is 6D series. Period number 4, period number 5, 6 and 7. All of you have understood? But in reality, this will be the scenario. What is happening? What you can observe? Compared to here, what you can observe? There is almost similar atomic size when it comes to 4D and 5D. Almost similar atomic size present between the 4D and 5D. Right? So this similarity in the atomic size of 4D and 5D is resulted due to the Lanthanoid contraction. The similarity in the atomic size of 4D and 5D is resulted due to the Lanthanide contraction. So what do you mean by Lanthanoid contraction? If you observe it carefully, I have told in the beginning itself. So in the 5D and 6D series, before entry of the 5D and 6D electrons, there will be filling of F subshell electrons. So for example, before 5D, 4F is going to get filled up. Before 6D, 5F is going to get filament. Right? Now based on the shielding effect, now what is happening here? If I take this one as the element, now I have 1, 2, 3, 4. Okay, so we have fourth energy level. So that is 4F is present here, then 5D is present here. Right? Now, since F subshell electrons will have the very less shielding effect on the outer shell electrons. Once again I will repeat. Since F subshell electrons will have the very less shielding effect on the outer shell electrons. When F subshell will start? When you are going with element where outermost energy level will be 6. Then only 4F will come. Please remember, for D subshell it is n minus 1. For F subshell it is n minus 2. Right? So why? Because energy level 6, then only 4F will come. So therefore, when we are talking about F subshell electrons, they will be having less shielding effect on the outer shell electrons. Fine? And to same extent even 5D, which will be having less shielding effect on the outer shell electrons. But 4F will have very less shielding effect. So due to the less shielding effect by the F subshell electrons on the outer shell electrons, there will be contraction in the atomic size. There will be decrease in the atomic size, or I can tell atomic size is not going to increase as expected. That is because of the less shielding effect shown by the F subshell electrons. So in which particular series F subshell will come? It will come only in 5D and 6D series. At present we are talking about 5D series. So due to the less expansion in the atomic size, due to that atomic size of 4D and 5D will become almost same. There will be slight increase in the atomic size. That's why it is called as Lanthanide contraction. All of you have understood? So you can expect question on this Lanthanide contraction. What is Lanthanide contraction can be the question, or what is the effect of lanthanide, or what are the effects of lanthanide contraction can be the question. Anyway, now at present today I have discussed about what do you mean by lanthanide contraction. In tomorrow's class we are going to discuss about what is the impact. What will happen due to the lanthanide contraction? That's what we are going to discuss in tomorrow's class. Any doubt? Any doubts? So what we have discussed here is, we have discussed about what you mean by D block elements, what you mean by transition element, or why they are called as transition elements. Then we have discussed about different series present in the D block elements. Then we have discussed about pseudo transition elements, right? Then we have discussed about physical properties, where transition elements will dominate over the S block element with respect to their metallic character. That's what we have discussed. And finally, very important concept we have discussed, that is Lanthanide contraction. Okay, so anyway, I'll stop here. Tomorrow we are going to continue with the class, and once again please inform to your friends to attend the live class. No other options. So regular class we don't know when it is going to start, so try to attend live class. Thank you very much.